So here's an example, integral from 1 to 2 with respect to y, and from 1 to y of x cubed y dx dy. So we're going to draw the region just because it's good to practice drawing the region for a couple reasons. And then we'll evaluate. So when drawing the region, I always look at the inside part first. So looking at the inner integral, so specifically for the region, I'm kind of ignoring the actual integrand. I'm just looking at this. And so I'm noting, first of all, that the dx part right here, right? This being paired with that means I really have x equals 1 to x equals y. Right, those are my inner functions. And I know it's x equals because it's going with the dx. I also know it's x equals because I have the y variable in there. It couldn't be y equals y. That wouldn't really, I mean, it could, but it wouldn't make sense. And then the outer one, of course, is going to be y equals 1 to y equals 2. Or, yeah. When I draw this, from here. So I'm always drawing the inner one first because those are the ones that actually have to be the functions, whereas the outer ones are just kind of telling you how far down to how far up, or how far left to how far right, depending on if it's dy or dx. So I'm going to draw x equals 1, which looks like this. And x equals y, which is the same as y equals x, which looks like this. Now, if we weren't paying super careful attention, we might just think it was this region down here. It's not, because then if we look at, well, first of all, we know that x equals 1 should actually be the left boundary, and x equals y should actually be the right boundary. So it's probably up here, and the y going from 1 to 2 confirms it. This point here is the point 1, 1, and then if we go up to y equals 2, we see that we're going to be bounded up here like this. So this is actually the region we're describing. I would mention that y equals 1 isn't really a boundary, right? Because that y equals 1 line we could draw doesn't really bound the region. It's just where we're kind of starting.
So why is it that and not the like bounded by the x equals 1, y equals? Oh, because I have
Sure.
I shaded in the area below.
Okay. So I will just draw it in red here just to kind of like counterpoint. So that region there, that could be described as the integral from sorry. Oh, sorry. So the other side of x equals 1. So like, okay. So just for those of you that might be watching this later, the reason it wouldn't be this region down here is because that region down there would be, well, first the left function would be x equal to y, the right function would be x equal to 1, and then the lower bound would be y equal to 0, and the upper bound would be y equal to 1. Or I should say it goes as low as 0 and as high as 1. So that's what that would be, in case you're curious as to why they're different. So then to evaluate this thing, right, we're just going to do the usual kind. Well, usual is probably, I should say, it feels usual to me because I've done it for so many years, but we'll do what we are going to be doing a lot, which is first we're going to integrate with respect to x. So we're going to anti-differentiate. This is going to get kind of gross because I picked funky things. That's fine. So we're going to do the inner integral first, as we always do, or will always do. And the antiderivative with respect to x of x cubed times the constant y is going to be x to the 4th over 4 times the constant y, evaluated from 1 to y. And then we still have the outer integral. Right? So that's all the stuff that's in the inner integral. And we still have the integral from 1 to 2 of dy. This is where I might choose to write that's x equal to y and x equal to 1. So I know I'm plugging in those things for the x's, not for the y's. So I'm going to then write this as still the integral from 1 to 2. And then I'm going to plug in y for x. I'm going to get y to the 4th over 4 times. I might just factor out the 1/4. I should have done that in this step. Oh, well. And then, so y to the 4th over 4 times y. Minus, if I plug in 1, I'm going to get 1 to the 4th over 4 times y. I would take the step of factoring out the 1/4. And then when I simplify my integrand, I have y to the 4th times y, which is y to the 5th. And minus 1/4 times y, but I factored out the 1/4, so I have just a minus y. And then we integrate as usual. The antiderivative of y to the 5th is what? Oh, don't forget the 1/4. We get y to the 6th over 6 minus y squared over 2 from 1 to 2, and then we plug in. So we get 1/4 times 2 to the 6th over 6 minus 2 squared over 2 minus 1 to the 6th over 6, which is just 1/6 minus 1/2. And we could simplify this, but I don't think there's a lot of point to simplifying it. Yeah, that's how that would work out. Let's look at an example of maybe an application here, just because sometimes questions like this come up. So yeah, like of course, read if you have questions, stop me. Let's say we have the following. The amount of rainfall per year in the triangular region, the Bermuda Triangle, no, the triangular region, bounded by these vertices, a 1, 0, 5, 0, and 5, 4, is given by the function of x and y equal to 4 over x times y plus 1 inches. Find the total amount of rainfall for the year in the region. So again, this function is telling you how much rain is falling at a particular point, and we want to find what the total amount of rain that's falling over the entire region. Okay, so we need to draw the region. My vertices were 1, 0, 5, 0, and 5, 4. So here's my triangular region. It happens to be a right triangle, which is probably good. So it's totally up to us to decide which way we want to do this. Do we want to use a horizontal strip so I should point out in the previous problem, the way we're describing this region is with a horizontal strip, right? We are going as far right as x equals y, as far left as x equals 1, and then the strips are going as low as y equals 1, as high as y equals 2. So when you're doing a dx dy, it's a horizontal strip. On the other hand, if you do the vertical strip, it's going to be a dy dx. And I say we might as well use a vertical strip because all other things being equal, we're used to thinking of things as functions of x more than we're used to thinking of things as functions of y. So I would draw a vertical strip. Say, okay, for my volume of rain, the inner integral is going to have a lower bound of y equals 0 and an upper bound of y equals, I need to find the equation of that line. It looks like, well, I could find the slope, right? The slope of that line is, let's see, difference in the y's over difference in the x's. Yeah, the slope is 1, no surprise there. And then if I use the x-intercept, I'm going to have y minus 0 equal to 1 times x minus 1, or in other words, y equal to x minus 1. So that's the upper boundary of my vertical strip there. Okay, here's the question. Is it dy or dx that goes with this inner integral? Yeah, because it's y equals. Also, what that means is we're going to integrate with respect to y first. We're going to anti-differentiate whatever y's we have, and then we're going to plug in x minus 1 for those y's, and the remaining thing will have x's in it. So yeah, that makes sense that we would do it in that way. And then we're going to talk about how far left and how far right this thing can go. Well, this thing can go as far left as 1 and as far right as 5. So we're going to go from x equals 1 to x equals 5. Dx. And then, of course, inside here, I should have the function I'm actually integrating. So writing this in the more typical way, it's going to be the integral from 1 to 5 of the integral from 0 to x minus 1 of my function 4 over x times y plus 1 dy dx. And if I was trying to make this maybe easier to handle, I might try to kind of break apart, meaning specifically through multiplication or division or kind of factoring, I guess is the word I should really be using, the y parts from the x parts. So if I know I'm going to integrate with respect to y, I might rewrite this as the integral from 1 to 5 of the integral from 0 to x minus 1. I'm going to say I've got a 4 over x times a 1 over y plus 1. Because then I can just kind of treat that 4 over x as a constant and integrate the 1 over y plus 1 using my usual methods of integration. And we're going to get, let's see, so the integral from 1 to 5. Can I fit this in here? Maybe. Sure. And then when I'm going to get a 4 over x, that's my constant. And then what's the integral of 1 over y plus 1? The natural log of the absolute value of y plus 1. From y equals 0 to y equals x minus 1. Dx. Something I wanted to say here. You could get away without writing the absolute value here because y is always positive, or I should say y plus 1 is always positive, but it's totally fine to write the absolute value as well. We're going to plug in, and we're going to get the integral from 1 to 5 of, I've got my 4 over x. I'm going to have the natural log of x minus 1 plus 1, so that's just going to be the natural log of x minus the natural log of 0 plus 1, which is just the natural log of 1, which is 0. Now you'll notice I didn't write the absolute value there, and that's because just like y plus 1 was always positive, x is also always positive, so we're totally safe to not write the absolute value. So now we've got the integral from 1 to 5 of 4 over x times the natural log of x dx. This is a great time for a u sub. Well, it's not just a great time. We have to do a u substitution. There isn't really any other way to do this. So we're going to let u equal the natural log of x, du equal 1 over x dx. So I see that this is looking like the integral of 4 times u times du. All right, my 1 over x dx, that's my du. And then I'm left with a 4 times natural log of x, which is a 4u. And I would change limits of integration. It's certainly not required, but I like to, so I don't have to do something silly like, right, like x equals 1, x equals 5. I'm just going to change this to, well, if x equals 1, then u is the natural log of 1, which is 0. And if x equals 5, then u is going to be the natural log of 5, which is the natural log of 5. So then we anti-differentiate. The antiderivative for u is 2u squared, or 4u squared over 2. And we plug in our limits of integration, 0 to natural log of 5. And we get 2 times the natural log of 5 squared minus 2 times 0. And that's going to be cubic inches of rain. The nice thing about changing your limits of integration is we don't have to change back to x. So I will just say, or actually I'll just write down here just so you can see why I think this is better. If we had gone the other way, like if we had said, I don't want to change these, and I'd done it as the integral from x equals 1 to x equals 5 of 4u du, and then gotten 2u squared from x equals 1 to x equals 5, which is then going to be 2 natural log of x squared from x equals 1 to x equals 5. We're going to get the same result. It just feels a little messier in my opinion. We're going to get 2 times natural log of 5 squared minus 2 times natural log of 1 squared, but that's just 0. So we get the same answer. I just feel like it's not as nicely done this way, but you can do it either way you want. So make sure that if you're doing it this second way, that you're very clear that these are x limits while your integral is still a u integral. Some people just don't write them at all. I prefer to write that they are whatever the original one was. But definitely, it's not okay to just write this, because then you're kind of displaying that you don't recognize that those are different limits of integration. So that's not okay. That's fine. Or just writing it as the integral without limits of integration is also okay, although I'm less of a fan of that. Cool. So let's look at what I feel like is kind of the most important part, or the thing that we often are required to do with double integrals, and that's sometimes we have to change the order of integration. So sometimes we must change the order of integration to be able to integrate. Here's an example. We're going to do the integral from 0 to 2 of the integral from 1/2 y to 1 of e to the x squared dx dy. And I know I've said it before, but I'll say it again. E to the x squared or e to the y squared on its own is a function that does not have an antiderivative that we recognize, right? Like it doesn't have what's called an elementary function as an antiderivative. There is some complicated antiderivative. It's literally just the integral written as the integral of this thing is the antiderivative, but there's not like a nice like 2x times e to the x squared or something like that. It just doesn't, there isn't anything. So we can't do this as is because I can't anti-differentiate this with respect to x in any recognizable way. But if we change the order of integration, then we can certainly anti-differentiate it with respect to y first, and then maybe something nice will happen. So to be able to change the order of integration or reverse the order of integration, we have to draw the region of integration to be able to reverse the order. This is where it's really important to know that, okay, since this is a 1/2 y to a 1, that's got to be an x equals 1/2 y and an x equals 1. And then the outer limits must be a y equals 0 to a y equals 2. We also knew this because it's a dx there. So dx here means it's x equals. dy out there means it's y equals. All right, so x equals 1/2 y. I'm really in my head thinking about as y equals 2x. So here's my x equals 1/2 y, or y equals 2x. And then x equals 1 is my nice vertical line. And then y is going to go from 0 to 2, which is where I imagine these two things are intersecting each other, right? Typically, if they're describing the region, it's going to be somewhat kind of straightforward. But if we check here, if x equals 1, then y equals 2x, then y is going to be 2. So this is the point 1, 2. So here's the region we've described. And the way the integral is currently written, we've described it using horizontal cross sections. Right? We're going as far left as x equals y 1/2 y to as far right as x equals 1. And then those are sliding from 0 up to 2. So we're going to change it and use vertical cross sections. So now I'm thinking, okay, for this vertical cross section, my bottom is y equals 0 and my top is y equals 2x. And then it's going to go as far left as x equals 0 and as far right as x equals 1. So this integral, we can rewrite as the integral from x equals 0 to x equals 1. And then y is going to go from y equals 0 to y equals 2x. And then we're going to integrate e to the x squared dy dx. And now we can do it, because if we integrate this thing with respect to y, well, there's no y's in there, so that's just a constant. So we're gonna get the integral from 0 to 1 of e to the x squared times y from 0 to 2x. Then we're gonna plug in for y. So we're gonna get the integral from 0 to 1 of e to the x squared times 2x minus e to the x squared times 0. I didn't even really need to write that term. So now I've got the integral from 0 to 1 of e to the x squared times 2x. And that's totally a u substitution, right? If we let u equal x squared, du is exactly 2x. So that integral looks like the integral of e to the u du. Oh, sorry, dx, du is 2x dx. Don't forget the dx now. And that's just going to be e to the u. So sometimes I kind of like to do the u sub off to the side and not actually change anything. So I'm kind of doing the opposite way I did last time and saying, well, my integral is going to be e to the x squared. And I didn't change the limits of integration. It's totally fine. I will point out that if I had changed the limits of integration, they would have still been 0 and 1. So I end up getting e to the 1 minus e to the 0, which is e minus 1. Cool. So that is a lot of what these problems end up having people do, is changing the order of integration. It's probably what most teachers consider the more interesting part of double integration, is having to do this kind of thing. So let's look at another example, which I think is before. Let's say we want to do the integral 0 to 2 of the integral from x cubed to 8 of 9x to the 8th over 1 plus y to the 4th dy dx. And so if I'm thinking of this as, if I was thinking of this as like two separate parts, I'm kind of thinking of this function as 9x to the 8th times 1 over 1 plus y to the 4th. Just kind of think of like the y separate from the x's. And if I was going to integrate this with respect to y, again, we could try, but there isn't a way of integrating 1 over 1 plus y to the 4th. At least not with methods we have. I'm trying to think if there is a way of doing it with other stuff, but I don't actually know, and that's not the point. The point is that it looks really hard to do it this way. So even then, this is actually what I should say, kind of like in 16b, where we were learning how to integrate, and someone could just like ask you, integrate this thing, and you had to figure out what method of integration to use. Someone might be like, here's a double integral. I'm not going to tell you have to reverse the order of integration, but you might have to. So we have to look at this and be like, well, this looks like it sucks, so I should try reversing the order of integration, because that's probably the way to go. If it doesn't seem straightforward to integrate using u substitution or integration by parts right off the bat, I would say consider reversing the order of integration. Okay, so I'm going to draw this thing. All right, so let's see here. So I've got y equals x cubed to y equals 8. So y equals x cubed looks like, this. And y equals 8 is just a horizontal line. And I know that these intersect at the point 2, 8. Because I said x cubed equal to 8, I get 2. And then we can see that x is exactly going from, I should say, and these are my vertical, right? I've got vertical strips. And x is exactly going as far left as 0, as far left as 2. Sorry, as far right as 2, apologies. So we're getting this whole region here. But then, of course, to change the order of integration, we're going to change the kind of strip we're using. So instead of a vertical strip, we're going to reimagine things with a horizontal strip. My right boundary is y equals x cubed, but I have to change which variable I'm solving for. So it's going to be x equal to the cube root of y, or preferably x equal to y to the 1/3. And my left boundary is x equal to 0. And then we're going to go as low as y equals 0 and as high as y equals 8. So my new double integral with the order reversed is going to be the integral from, so y is going from 0 to 8 And x is going from 0 to the cube root of y, or y to the 1/3. And now I'm still going to have 9x to the 8th times 1 over 1 plus y to the 4th. But these have switched order, right? That's the whole point. Instead of dy dx, now it's dx dy. And now we can certainly integrate with respect to x, because the integral of 9x to the 8th times the constant is just x to the 9th times that same constant. So let's do that. So we're going to get, the integral from 0 to 8. The integral of x to 9, of 9x to the 8th is x to the 9th. So I kind of like to put the constant part out in front. So I've got my constant, 1 over 1 plus y to the 4th. And then I've got my x to the 9th evaluated from 0 to y to the 1/3. I do recommend writing x equals here and x equals here, just because it really helps me remember where I'm actually going to plug that in. I mean, here it's I guess if these are both constants, it'd be more important. Since I have a y to the 1/3, I know I shouldn't be plugging in y to the 1/3 for y, which makes it easier to remember that I'm doing it for x. But you can have double integrals where it's like 0 to 2 and 0 to 5, and then it can be like, we should be extra careful. So plugging this in, we have the integral from 0 to 8 of 1 over 1 plus y to the 4th times y to the 1/3 to the 9th minus 0 to the 9th. And of course, y to the 1/3 to the 9th is y to the 3rd. So this is it. So a lot of these problems, when you change the order of integration, end up working out that after you do the first integration, the second integration becomes a straightforward u substitution. That's a very common thing that happens with these. So we're going to get the integral from 0 to 8 of y cubed over 1 plus y to the 4th. And then we're going to do the u sub. We're going to let u equal the denominator, y 1 plus y to the 4th. Ooh, my numbers are going to get big here. That's okay, it happens. And my du is going to be 4y cubed dy. I know we used to do that. I really like doing it the way I like doing it though. So I'm going to say 1/4 du is equal to y cubed dy. So there's my 1/4 du. And then the denominator is just u. So we're going to get the 1/4, I'll put that in front, du over here, and then I have a 1 over u. And I guess we could change the limits of integration. If y equals 0, u equals 1 plus 0 to the 4th, which is 1. And if y equals 8, u equals 1 plus 8 to the 4th power. Which I guess we could write down. It's 1 plus 2 to the 3rd to the 4th, which is 1 plus 2 to the 12th. And I always remember that 2 to the 10th is 1024. So 2 to the 11th is times another 2, which is 2048. 2 to the 12th is times another 2, which is 4096. When you play stupid games on your phone for a while, you get to know these numbers pretty well. So that's going to be 4097. Which, yeah, looks kind of silly, but whatever. So then we have 1/4 times the natural log of the absolute value of u from u equals 1 to u equals 4097. And then we're just going to get 1/4 times the natural log of 4097 minus 1/4 times the natural log of 1, which is a 0. If you left this as 8 to the 4th plus 1, that would also be totally fine. Yeah, which is definitely what Grant did in the solutions here, which is smart, right? You want to try one on your own, Reed? You want me? Sure. So for those of you in class and for those of you at home, take a minute to try this next one on your own. So try number 5, the integral from 0 to 9 of the integral from the square root of y to 3 of 1 over the square root of x cubed plus 9 dx dy. And clearly the point is you're going to have to reverse the order of integration. So I'll give you a few minutes to work on that. I will use the restroom while you work on that. Okay. Feeling good, Reed? Cool. So, right, our original region, our inner limits of integration are x equals root y to x equals 3. So I drew x equal to the square root of y, or y equal to x squared, and x equal to 3. And I was careful about it. I was like, oh yeah, I know my left boundary is x equal to root y, my right boundary is x equal to 3. And then typically, unless someone's done a bad job of writing the problem, usually the other limits of integration will kind of nicely describe the region. So right, we're going from y equals 0, which gives you like the typical boundary, to y equals 9, where they exactly intersect. This would be gross if we went to like y equals 8, because then the top would be that, and then describing it the other way becomes much more problematic. So usually if they've done this right, it's not going to suck. For reversing the order, we want to use this red strip now for, so when I think about the strip, I'm really thinking about that being the limits of integration for the inner integral. So my left to right strip, my limits of integration were x equal root y to x equals 3 for my inner integral. For my vertical strip, my limits of integration are y equals 0 to y equals x squared. And that's of course going to be a dy. And then my x values are just, well, my strip can go as far left as 0 or as far right as 9. Yeah. And then that's my dx. And then I've got the same function, 1 over the square root of x cubed plus 9. Typically, again, I'll say if something looks like something you've never been able to integrate before and you're asked to integrate it, it usually means you're supposed to change the order of integration. I'm fairly certain this is another example of a function that literally cannot be integrated. So if something seems like it's really, really terrible, it's probably something where you need to change the order. So now if we integrate this, we're just going to get a y. So I'm going to get the integral from x equals 0 to x equals 9 of this thing anti-differentiated, which is going to be y over the square root of x cubed plus 9. Or you could do 1 over x squared times y, whatever you like, from y equals 0 to y equals x squared. Plugging in the y equals x squared, we're going to get the integral from 0 to 9 of x squared over the square root of x cubed plus 9 dx minus 0, right? And then we do a u sub, which is typical. So we're going to let u equal the x cubed plus 9. It's also going to be a big number. Du is going to be 3x squared dx. So du over 3 is going to be your x squared dx. So I would rewrite my integral as the integral. Well, I'm going to have a 1/3. There's my 1/3 du. So I'm going to have 1/3 du of 1 over the square root of x of u, or right, 1 over the square root of u. And then my values are going from, let's see, well, if x is 0, u is going to be 0 plus 9. And if x is 9, u is going to be 9 cubed plus 9. And 9 cubed is 729, so we get 738. Why do I know this? I don't know, because I've seen 9 cubed so many times in my life. It's just a number. Actually, there's a really famous story involving 9 cubed, so that's actually probably why I really know it. But I should a famous math story, which I'll tell you in a minute. So then this is going to be super gross. This is u to the negative 1/2. So the antiderivative is going to be u to the positive 1/2 times 2, so times 2/3. And then we're integrating from 9 to 738. So we're going to end up getting 2/3 times the square root of 738 minus the square root of 9. And while I could distribute the 2/3, I don't really feel a need to. There's our answer. Cool. Let's see. I feel like there's one other thing I wanted to mention here. Yeah, we could do that. We could do that. So back to that rainfall question for a second. So let's revisit the rainfall thing, because there's one thing I want to say about it, which is something that's not going to be surprising, but is just worth mentioning here. So revisiting the rainfall question. Revisiting rainfall. We found that Let me just look at it here so I can see it. All right, so we found that the amount of rainfall on this region, which I'm just going to draw, the head vertices 1, 0, 5, 0, and 5, 4. We found that the amount of rainfall on this region was, we got 2 natural log of 5 squared cubic inches per year of rain, because it was the amount of yearly rainfall. So a question sometimes people ask, especially for the, and I should also mention where the rainfall was given by f of x comma y equal to 4 over x times y plus 1 inches per year, I should say. So just to kind of think about what's happening here, it kind of makes sense that we're getting cubic inches, because we're saying we're getting so many inches of rain, and then we're kind of multiplying or integrating. We're multiplying that inches of rain by the amount of area in here, kind of. So an area, which is measured in inches squared, times the rainfall, which is measured in inches, should give us a volume of rainfall in inches cubed. But what people sometimes like to ask about a question like this is, what was the average rainfall? Meaning, if you picked a little like square inch of this, what would the rainfall be in that square inch? And so it's exactly what you think it would be. You're just going to take the total amount of volume of rain and divide it by the area of your region. So just like average value before was the integral divided by the length of the interval, average value or average value of a function for a double integral is the double integral divided by, instead of the length of the interval, the area of the region. So we're just going to get the average value, average rainfall, is going to equal the double integral that we did, which was the integral, which I'll write down again just for the fun of it. It was the integral from 1 to 5, the integral from 0 to x minus 1 of this silly function 4 over x times y plus 1 dy dx over, there's a couple ways you could write this. I typically just like to write it as the area of the region. And we can totally find the area of this region really easily just using geometry, right? It's going to be 4 or 1/2 times 4 times 4. So that's going to be our 2 natural log of 5 squared divided by 1/2 times 4 times 4, which is 8. So you're going to end up getting, if we reduce this, the natural log of 5 squared over 4, because I cancel the 2. That's it as far as average values go. A couple things to say about this. So it's easy if the region is a normal geometric shape. If it's a triangle, you shouldn't be doing anything other than do like base times height times 1/2. It's a rectangle, base times height. It's a circle, great. The area of a circle, pi r squared. But more generally, we can say that the average value of a function of 2 variables, x and y, over some region R is just the double integral over that region. And this is how we write a double integral when we don't know which order we're doing it. We just say dA, where dA is either dx times dy or dy times dx, whichever one makes more sense. And then we divide by the area of the region, which, again, if it's easy to calculate using geometry, we should do it that way. But if it's not easy to calculate using geometry, then what we do to find the area of the region is we just do the exact same double integral on the bottom, except we do the double integral of 1, because that's how you find the area of a region using a double integral. So, for example, we could be asked to find, let's see, I had one here, no, I lost it. Sure. Sorry, it's going away. It's all going away. For example, find the average value of, yeah, sure, we'll do this one. F of x, y equal to, yeah, 2y times cosine of x on the region described by, let's see, region bounded by, let's see what we got here. Y equals 0, y equals square root of x, and x equal to pi over 2. So let's draw the region. I mean, I know I'm going to be doing a double integral over this region of this integral. Well, let's see. So if I draw my region, y equals 0, y equal to the square root of x, and x equal to pi over 2. Here's my region. And it doesn't seem like, so before I write my integral, I might look at the thing I'm going to integrate and try to decide if doing it one way versus the other way is better. Here, it looks like integrating either function first should be fine. I don't actually know. But let's go ahead and let's write it like we don't know better. So I'm going to use a vertical strip because that is my usual, right? If all other things are equal, I go for a vertical strip because that's just what I'm used to doing. Using a vertical strip, I'm going to write this as the integral from, I do the inner part first. So from y equals 0 to y equals square root of x, and then dy. And then x equals 0 to x equals pi over 2 dx. And we've got a 2y cosine of x. Okay, this seems probably just fine. So we do that this way, we're going to get the integral with respect to y. So we're going to get a y squared times cosine of x from y equals 0 to y equals root x. And then that's the inner part. And then we're going to do the integral, whatever that is, from x equals 0 to pi over 2. So we've got, let's see, the integral from 0 to pi over 2 of square root of x squared is just x. So x times cosine of x minus 0 times cosine of x. And now we have to use integration by parts. So real quick over here, if I let u equal x, dv equal cosine x dx, du is 1 dx, v is equal to sine of x, then I'm going to get x sine of x minus the integral of sine of x, which is going to be x sine of x plus cosine of x. Plus cosine of x? Yeah, plus cosine of x. Yeah. The reason I'm kind of trying to do that all here is I don't love writing out my integration by parts with the limits of integration kind of in all the places. So I'm going to say this is x sine of x minus a minus is plus cosine of x. And then I can go back here and be like, okay, great. That's going to be x sine x plus cosine x evaluated from 0 to pi over 2. And I'm going to get pi times sine of pi over 2, sorry, pi over 2 times sine of pi over 2, which is 1, plus cosine of pi over 2, which is 0, minus 0 times sine of 0 is 0, plus cosine of 0, which is 1. So I end up with pi over 2 minus 1. And that, for lack of a better description, is the volume under this function over this region. But if I want to find the average value, I then have to find the area of this region. So, oh, it's 1053. Sorry, you should have said something. Read. So just real quick, the area here is just going to be the same double integral, except way easier because we're just integrating 1. So then if I integrate 1, I get y. And I plug in root x minus 0, so I get root x. And if I integrate that, I get x to the 1/2, so x to the 3/2 times 2/3, 0 to pi over 2. So I end up getting 2/3 pi over 2 to the 3/2, which is kind of funky. But then just to finish the problem here, the average value would be this number divided by that number. So here, just there's nowhere to write it. Fine, there's another piece of paper. So my average value would be is going to be the pi over 2 minus 1 divided by the 2/3 pi over 2 to the 3/2. So if your region isn't something nice like a triangle or a square or a rectangle, then you actually have to do the double integral of 1 to find the area. But it's usually not too terrible. So. All right.